Hey there, this is Horner, and this is the 2000 AP Physics C Mechanics #1 question. This one is on oscillations. You're conducting an experiment, and you're finding the acceleration due to gravity at an unknown location. So they call that G with a lowercase u that is a subscript. In the measurement apparatus, a simple pendulum swings past a photo gate located at the pendulum's lowest point, records the time for the pendulum to undergo 10 full oscillations. So a pretty easy thing for it to do. The pendulum consists of a sphere of mass at the end of a string that has length L. There are 4 versions of this apparatus, each with a different length. All 4 are at an unknown location, and the data shown below are sent to you during the experiment. We actually are missing one in this data table, so we'll add it as we go through. But the very first, let's go ahead and add that since we've boogered it and it's not there. So there should be another one here of 21. So we'll put that, and then this is 10.09. So there is our other data point, and then what we'll do is let's make, since this program is so screwy now. Okay. They want you to go through, calculate the period, and the square of the period. Use a reasonable number for significant figures. Notice that these have 3, this one is 3, 4, 4, so I would say that we either need 3 or 4 places past the decimal. So let's just do 3. They're not real picky, but if you didn't do any, or if you did 12, that would be a problem. This is the time for 10 swings. We only want it for 1, so we're just got to divide each one of these by 10. So this is going to be 0.762. Next one's going to be 0.889. I'm actually going to move this one down here. It's 1.009, and then the last one is going to be 1.208. So now that we have those 4 points, let's go ahead and square each one. This one is 0.581. Next one is 0.790. Then 1.018. And then finally, that's a 1, sorry. And then our last one is 1.459. So that we've done that, they now want us to go through and plot the square of the period versus the length of the string. So let's go through and do the best that we can to try to get these. Our very first one here is at 12, so that's pretty easy to see. And then we want 0.581, which is a little bit harder to see. So this is about 0.58, probably somewhere about right there. The next one is 18, so here's 18. And we will move up to about 0.790, so this would be 0.56790 would be about right there. Next one is 1.018, and that is at 21. So 21 and 1.018 is going to be probably somewhere about right there. Then we have another one, and it is way out here at 32. And it is 1.459, so we're almost at 1.5. So next thing we need to do is draw a straight line. We want to draw a straight line in order to see the, oh shoot, what do we want to see? We want to see the best fit line. So we want to make sure that we're trying to hit this majority of, a majority of the points. And so usually you can look at these and say, well, I got the same number of points above and below. So if I do that, I probably can do something similar to what you see here. And that would be a pretty decent best fit line. So now that you've done that, I can tell you that, let's talk about some points here. One of the points that you get in part A is for solving all of these correctly. And so we've done that. You get 1 point for squaring everything. For putting in 2 to 3 decimal places, we got that point. And then for doing the whole table. Some people didn't do the whole table. They forgot to do this, even though it explicitly says to do it. So doing the whole table is another point. So 4 really easy points. For this part, the points pretty easy to do too. This is for 3, so it is for plotting the numbers. For doing the straight line. If you do not use a ruler or a straight edge, you might not get those points, so be careful. And then drawing it so that it's an approximate best fit line. So we've done that. So that one is worth 3 points. And so we probably got another 3 points there. Now it says, assuming that the pendulum undergoes the small amplitude oscillations. So because of that, we know that it should follow simple harmonic motion. We shouldn't have any dampening or anything else. From your fit, determine the experimental value, G experimental, of the acceleration due to gravity at this unknown location. And they want us to go through, and it says justify our answer. So let's go through and just find the slope first. So we know that the slope here is going to be equal to the change in the period squared all over the change in the length. When you do that, there's going to be a wide variety of answers that you're probably going to get, but the typical average value that we were finding was about 4.50 seconds squared per meter. So most values are in between 4 and 5. So somewhere from 4 to about 5. So somewhere in that range, as long as you're there, you're good, but you would want to make sure that you show that. You need to just calculate it, and once you have it, you now need to say that period is equal to 2 pi times the square root of L over G. So now that we've done that, we can solve this equation for G. And we could say that, well, let's go through and do this. We know that the relationship between t squared and L is going to be t squared is equal to 2 times pi times L over G. And so if I want G, I need to say G is equal to 2 pi L all over t squared. But remember, our slope is t squared over L. So if we remember that, we could also say that this is 2 pi over our slope. So we need to find our slope first. Once we find our slope, take 1 divided by the slope, and then take 2 pi divided by that number. And that will give you the same type of thing. So your G experimental should be equal to 2 pi divided by our slope, because that would be 1 over the slope. And so that would be about 4.5. And if you do that, you are going to get something close to 8.77. Don't forget your unit, meter per second squared. So where do the points come from for actually showing and calculating the slope is where 1 point would come from for using the equation t is equal to 2 pi square root of L over G to recognize that it is a pendulum, for solving for an equation that will give you slope, and then finally for having an answer that is within reason. It says if the measurement apparatus allows a determination of GU that is accurate to within 4%, is your experimental value within agreement of that value of 9.8. So this is where we're getting into just trying to figure out how close are we in terms of experimental error. So let's go ahead and solve for that. It is 9.8 minus 8.77 divided by 8.77. Now notice this is percent error, and if we multiply that times 100%, we're going to end up with about 11.7%. So here we would say, and that would be greater, obviously. Okay, that is a pretty big one. So because of that, it is not in agreement with G. So no, not in agreement. So you get 2 points, you get 1 for showing that, and 1 for stating that no, it is not in agreement. Somebody informs you that the experimental apparatus is in fact near a surface, but the experiment is conducted inside an elevator with constant acceleration A. Oh yay. Assuming that your experimental value of G is exact, determine the magnitude and direction of the elevator's acceleration. So Let's think about this elevator for just a second. We know that we have an elevator. You've got a person standing on the inside. There's a cable pulling it up. And the elevator has a constant acceleration of a. So we know that that is its acceleration. This elevator has got to be moving either up or down. Okay, you just have to make it work so that everything comes out really well. So for this one, we know if we draw a free body diagram for our person, so this is for the person, we know down would be mg. We know that up on the person would be N. It is not tension, okay? So don't put tension there. The person is standing on the floor of the elevator. And they are accelerating. So let's just say that they are accelerating in the upwards direction. If that's true, that MA is going to be in the upwards direction. So that means that our positive is up. So now we're going to do an equation. N minus mg is equal to MA. So here we could say that N is equal to mg experimental is what we found. So our acceleration here is equal to g experimental, minus g. That will give us an acceleration of negative 1.03 meters per second squared, and that is directed upwards. So obviously the elevator is accelerating downward, hence why we have the negative. And that is the end of this problem.